We move on with the laser principles, amplifier bandwidth, the optics of lasers, frequency selection, and I will talk about intensity variations. So first, let's talk about operation of a simple laser. And we have talked about that the laser first has to have at least two mirrors to form the optical resonator, and in between we have amplifier over here. And what the amplifier is that in fact it amplifies the light. We have talked this about. Whenever there is an input to the amplifier, what it does, it either increases the amplitude of the light. In other words, it increases the intensity. Or if you view the light as particles of photons, then that it increases the number of photons. So in some lasers, the amplifier, the mirrors, just are at the end of amplifier. Okay, the amplifier endpoints are just processed so that the surfaces of the amplifier endpoints acts like a mirror. Or in some cases, like in this second picture, the amplifier is limited inside the region in between the two mirrors. For example, over here you see this is a typical amplifier cross-section for a helium neon laser. And what you see over here is that the amplifier is just inside the resonator, and its endpoints are not mirrors. Mirrors are separated, and this you have a funny cut-shaped amplifier region is because of the to reduce the internal reflection of the laser light on the surface of the amplifier. And I will talk about this in a application video separately. So this is the two possible configuration that you may have your amplifier just united with the mirrors at the endpoints, or you may have the mirrors are separated from the amplifier. So the next thing is, how does the optical amplifier works is that what you see over here, you can always picture the amplifier as a black box. You don't know what's inside the box, but you know what it does. So what it does is that, as an input, it takes the light of some amplitude and increases the amplitude as you see over here at the exit. So between these two lights, what the difference is that the output light has a larger amplitude in compared to input light. Larger amplitude means higher intensity output. But you may not know how amplifier does this, but what it does. So this is the typical picture that but what you see over here, that if you look at the the number of peaks in the amplifier, so in the input light, it doesn't change. In fact, what I'm trying to say is that the wavelength of the input light and the output light are just the same. The wavelengths and only things other than the amplitude doesn't change, but the amplitude is changing. Okay, so this is linear optic. I mean, if also some box or some device does change the frequency or the wavelength, then it means that it's a nonlinear optical device, but it's not our subject over here. So next thing is that as opposed to the amplifier, also we have absorbers. An optical absorber, it's again you can think of the optical absorber box as a box, and what it does is just it takes the input light as this amplitude and it reduces the amplitude. So that means it takes away some energy from the input light, it keeps it, and it leaves the rest again as some output light. But it absorbs basically, so it reduces the intensity, or it reduces the number of photons it takes. And if it takes like 10 photons at a time, and it leaves just like 7 photons at a time, that means it's absorber, because it's absorbed 3 of the photons of incoming light. So this is the picture that I'm talking about. I mean, if you look at the amplifier as in the microscopic level, okay, so in the atomic level, what I mean, what it becomes in atomic level. So in the atomic level, we picture the light as some number of photons, okay, and some number of photons. Let's say 2 photons are coming over here. So what happens over here is that, you see 2 pictures over here. You see 2 photons in the first picture. This is the first picture, this is the second picture. In the first picture, we have 2 photons, and we have 1 atom. And in the atom, you see these levels 1 and 2 labeled as 1 and 2, and this circular object which represents the electron, and these 1 and 2 represents this energy level of the electron in the atom. So what you see over here is that the electron is at the first level, or we usually say it's ground level, or the ground state. It's in the ground state energy, and the electrons can take different energies inside the atom, and this is only the simplest atom that you can see, that the electron has only two accessible energy levels. But of course, usually this number of energy levels is very high in even the simplest atom in hydrogen. There are many energy levels, 1, 2, 3, 4, etc. But we only picture the first 2 of these levels, okay? And what you see in the first picture is that the atom is in the ground state. That means the electron is in the lowest energy state. But that means, if electron has the possibility of going on the other energy levels, then it can do. And what you see over here in the first picture, that the electron is just occupies the first energy level. And there are 2 incoming photons. And if these 2 incoming photons, which looks like exactly the same wavelength and the same frequency, of course, if the frequency of these 2 atoms just matches the energy difference between the 2 levels, okay? I mean, what I mean is that if you think of the photon only as the energy packet, and the amount of energy of one single atom is just equal to difference between these 2 energy levels, if that is the case. I mean, usually in most general case, the coming photons may not have the same energy that the difference between the energy levels of the atom, but we are only thinking the case that these incoming photons has just the energy enough to match the difference in the energy levels of this atom 1 and 2. If this is the case, that means that when these photons just passes by the atom, which is in the ground state, since the energy of one of the atoms just enough to bring the electron to the upper level, then it does, okay? So it just absorbs one of the photons, and it uses its energy, so it just kicks himself to the upper level of the energy. So that what it means in the second picture is that 2 incoming photons, one is missing, but it's not in fact is missing. It's just used for transferring the ground state electron to the one higher level excited energy level. So I mean, in terms of quantum mechanics, this is quite possible. And this picture just tells you that one of the incoming photons is just absorbed by the atom. And the atom absorbs the energy, and when the atom absorbs the energy, it brings its ground state level electron to just the upper state, which is just a higher energy level. Okay, this is the absorption of light by materials in the picture of microscopic level. I mean, in the picture of quantum mechanics. So, and what you see over here is that, we have these energy levels of the atom, E1 and E2, just refers to the ground state energy, and the first excited state, if there are other energy levels which are higher than this second excited, the first excited, and then these are going to be, of course, labeled as 3 through 4, etc. And for the time being, just think about these only the first two levels, and always the first level is always known as the ground state. So, as I say, if you picture this light intensity in this graph for this process of absorption, okay, and this vertical axis refers to the intensity of light, and the horizontal axis refers to the frequency of the incoming photons. If the frequency of the incoming photons, here you see F12 in the frequency domain, or in the frequency axis, this F12 refers to specific frequency, optical frequency, which is just equal the energy difference between these two levels. I mean, there is a relation between this frequency and the energy levels, or the energy difference between these two levels, given by this. Okay, if you're able to see this equation, that F12 is a specific energy, and it just equals to the difference between the energy levels of the atom. But of course, the energy and the frequency are not the same physical quantities. Energy is, measured to be joules, and the frequency measured to be hertz. Since these are different, physical quantities, in order to match the units for these two, we just divide the difference of the energy by h bar. H bar is the Planck's constant. Let me put over here. H bar is the Planck's constant. Okay. And whenever we are talking about quantum mechanics, h bar is always there. Okay. Well, in fact, it's not h bar. It's h. H bar is related to h just by divide. If you divide h by 2 pi, it's h bar. We're going to use this h bar in when we talk about the angular frequencies. So we're talking about the linear frequency of the light. So, well, this case, when the incoming photons has just this energy, has just this frequency, that F12, which is just equal to the difference between the energy levels of the atom, we say that there is optical resonance. Okay, optical resonance occurs whenever there are some medium or atoms that they have in some of their energy levels just match up to the existent optical light frequency. Then we say that the picture just is in the resonance. So when this is the case, okay, the incoming intensity, which this flat part, refers to the incoming intensity. And then in that case, if these two photons just meet with the atom at the resonance frequency, then we just go down to this point, that the original intensity of the incoming light just reduces this amount. Well, it doesn't touch or doesn't become zero, because we still have existent photons in the medium. Okay, not all photons are absorbed, because you see over here one of the photons is just there. So that's why this dip does not touch to the zero intensity, and just takes its minimum value. But it only happens not. You can think that this drop down of the intensity must be. You might think that only happens exactly at this frequency. But if you look at carefully over here, what happens just in this region, that the frequency of the photons does not match up at all. But if it becomes close to the value, it might be somewhere over here. And somewhere over here, the frequency is not exactly equal to f12. What happens in that case? What happens in that case? Still, there is chance of absorbing the incoming photon by the atom, even if the incoming photon frequency does not match exactly, but it just, it closes. It just approximately closes to the energy gap. Still, it catches. I mean, still it can be absorbed, but the absorption will not be a maximum right at the resonant frequency. If you are off resonance, there is still chance of absorbing. I mean, that means the absorption, you have the absorption bandwidth, okay? You have this range of frequencies which is centered around f12, and you have some frequency values there. Still you can have the chance of absorbing, but the absorption is not 100% probable. You have some probability, but if the frequency exactly matches up to the f12, then the absorption occurs. But if not, in that case, what you obtain in the spectrum is that you will have some bandwidth of the absorber. Okay, this is absorber. Yeah, you have the bandwidth of the absorber. Okay, and this bandwidth, it will be pictured like this bell shape, inverse bell shape. Okay, this is what I'm trying to say. All right. So over here, it's the same picture, but the picture is just the classical picture. I mean, you have just picture the incoming light as a pure wave, okay, not the particles. And if the amplitude is some amount, and you will see that the amount of amplitude will just drop down by absorbing some portion of it by the atom. Okay. All right. So I mean, there is no need to talk about more on this picture. Let's switch to the next. So over here, I will talk about two cases of absorption, and one case is called stimulated absorption, and the other case is spontaneous absorption. So what are the differences? Are there any two different types of absorption? And it appears yes. I will talk about this. So what is this stimulated absorption and spontaneous absorption? Okay, so what you see in this first picture is that, again, you have inside a medium, you have these atoms that you have two energy levels, you see. And in fact, you have many of these atoms. That's why you have many electrons over here. Every electron represents one atom, okay? Every circle over here is corresponding to one atom. And in this representation, we have 1, 2, 4, 6 atoms. And all of the atoms and electrons are in the ground state in this picture, okay? And there is also one incoming light of a certain frequency and a certain amplitude. If this incoming light, meets up with these atoms which are very close to each other, side by side, let's say, for example, and you will have the absorption of these light by the electrons, okay? Some of the atoms will kick their electrons from the ground state to the excited level, to the second state, by dropping the amplitude by a certain amount. I mean, if these number of electrons which are upgraded, which are sent to the second excited state, first excited state, then if there are more atoms like kicking their electrons to the upper level, the amount of drop down in the amplitude will be large. So what happens? What happens is that right after these electrons, for example, there are only 2 electrons or 2 atoms that absorbs this light by kicking their electrons in the upper level, the next thing that you might ask is that, well, are these electrons which are at a higher energy level will they stay there forever? Okay. Well, in microscopic world, this picture is like this. Whenever the electrons are getting to upper levels, they will not stay there for a long time. They always want to go back. And in fact, this is because of a principle that, every physical system tends to be in the lowest energy level. So that's why these electrons, as soon as they get there, they will go back to the ground state. And of course, since they change their energy level then, okay, when they go down, they lose energy, but this energy, loss of energy again, will be converted to photons. Okay, first of all, if you ask me what is the amount of time, how long will they stay there, it's typically in the order of nanosecond. Okay, so in the order of nanosecond, they will live on the higher energy level, but after some fraction of or some amount of nanoseconds, they will go back. When they go back, since they will lose energy, this energy will be radiated by creating photons in any direction. Okay, so if you ask that, okay, if these electrons are going down, what happens to the energy? And their energy will be, of course, will get lower. They will get the lower energy, but this loss of energy will be converted to photons. These photons are created photons when the electrons go from their excited level or higher energy level to lower energy level. The amount of energy which is lost by electron is converted to photons. Okay, this is what happens in the atomic world. The electrons are just creating photons when they lose their energy, and the frequency of the created photons will just be equal to the energy difference again. I mean, whatever the energy that they are getting to the upper level, when they go down, they will just create the same amount of frequency photons, just match up to their energy difference. Okay, if there are 2 electrons that loses their energy, there will be 2 photons created. Okay, one thing is that we usually call this type of emission, that we call emission, because electrons are emitting photons, okay, or atoms are emitting photons. This kind of emission is called the spontaneous emission, because if you ask me what are the directions of the photons, I mean, when they just lose, these electrons are losing energy. If the photons are created, because photons cannot stay at one point, they will move with the speed of light. But in which direction they will go? In any direction. Okay, they will just randomly choose any direction, this way, or this way, whatever. On average, if there is continuous spontaneous emission, usually the atom is giving off light in every direction, just looking like a spherical spherical light source. Okay, I mean it just acts like a light bulb. The light bulb just giving off light in every direction from a center. It gives light in every direction. So in spontaneous emission, what the atoms does is just the same. It will give off these photons in any direction, in spontaneously, in every possible direction. So what you see over here is that you have a vapor cell over here, what vapor cell is, acts like a medium of atoms which are initially in the ground state, and you have over here a detector that detects light, emitted light, and over here this orange box is just producing a light source, producing a light source of certain frequency, which is called, over here it's shown as F. Okay, let me put this F more clearly over here. We have F, but it's a variable. You can always change. Suppose that you can just adjust the frequency of the photons as you wish. When you send a certain frequency to this vapor cell, okay, and so that this frequency just matches up the energy levels of the atoms in the cell, what you see is that glowing light, although you just give the light in this direction, you will see the light coming out in every direction out of this vapor cell because of spontaneous emission. Okay, but also, since it gives off in any direction, also this light will be given off in this direction. But in this direction also you have the input light. Some amount of the input light might not be absorbed, and it just go through the vapor cell without any interaction, and just goes to this detector. What you see over here is that on this spectrum, that the vertical axis just refers to the intensity of light which is detected at this detector, and this axis just refers to the frequency of the source light. If we change the frequency so that just matches up the levels of the electrons in the atom, the drop down in the detector is maximum. The detector, if you send the light of frequency which is just equal to the F12, which is just matches up to the energy levels between the atoms inside the vapor cell, you will detect at the detector the lowest amount of light. But if this frequency is off this value, the amount of light at the detector will be at this level, which is the maximum. It's nothing but all of your input light, which is sent through this vapor cell, will be detected by the detector without any reduction, because the atoms inside the vapor cell will not absorb these frequency of photons, because it doesn't match up to the energy level. But whenever there is this frequency which is equal to the matching frequency, the detector will get the minimum value of signal, because some of the photons will just be absorbed by the atoms in the vapor cell. Okay, next what we see over here is that we see a optical amplifier. Why? Because this is again the first picture and the second picture. In the first picture, again, we have one photon and one atom, but this time the atom is having an electron which is in the higher energy level, not in the ground state. Okay, and the incoming photon has just the right frequency, that the frequency of the incoming photon matches the energy difference between these two levels. If this is the case, what happens? If this is the case, you might think that the electron will absorb further the incoming light and will go up. If there is any higher level, energy level, it will go up to this energy level. If there is no such a level that the frequency of this incoming photon will make the electron go up enough energy to make it go up in the higher level, what will it do is that it will bring the electron down. Okay, so this time the incoming photon will pull the electron which is at the higher energy originally down to the ground state. Okay, so If this is the case, then the electron will lose energy, right, by bringing himself down to the lower energy level. It will lose energy, and this energy loss will be converted to a photon. Okay, it will be converted to a photon which has just the right frequency, matches up with the difference between these two energy levels. Okay, so that means initially you just have one photon, but now you have two photons. So the photon number is just increased, and this is nothing but an optical amplifier. Okay, so this is what a quantum optical amplifier, how this quantum optical amplifier works. It just brings, if somehow, of course, you have some atoms which are excited. Well, of course, you can say that usually, most of the time, if you have a medium of atoms, they're all tend to be at the lowest energy level. But if you somehow gave them energy so that their electrons are at the higher energy level, when they are at the higher energy level, at this time, if they see these coming photons, these photons will just increase their number in response to this case. So this is an optical amplifier, and it just increases the number of photons by this way. So in the next slide, what you see over here is that you have an optical amplifier, and the optical amplifier, you have this incoming photon of frequency which is at this level. Okay, but since you have in the medium there are atoms which are at the higher energy level acting like an optical amplifier, if you send just a photon which is just at this resonance frequency that matches up the energy level between these two energy levels, the difference between the energy levels, then you will see that the intensity of the photons in the medium will just increase to this level, peak. Well, in the picture, you will see that it is clearly seen that the number of photons just increases because the intensity is now higher. Okay, of course, if this incoming photon frequency is not just matches to the energy difference between these two levels, there will be no any absorption. This photon will just passes by, and there will be no change of electrons, let's say level. Well, the one thing is that still this electron may, of course, lose its energy, right? But this energy loss will produce a photon which has some certain frequency which is not equal to this frequency, incoming frequency of the photon. I mean, at the resonance, what we see over here is that since originally we have just sent a resonance photon, if we send a resonant photon, the produced photon, because of electrons coming down, will be such that just equal to the incoming photon, and also its phase is going to match up with the incoming photon. What I mean by phase matchup is that, you see over here one photon, but one photon will have certain phase, of course, because it's an electromagnetic wave. Let's say picture that photon wave like this. Then the produced photon, because of the electron coming down, will produce a second photon just matches up the same matching peaks and dips. That means, if you see these two waves like one top of each other, you can see that these are in phase. Why? Because when one wave is at the peak, the other wave is at the peak. When one wave is at dip, the other wave, it's just the same phase, exactly one copy of each other. There is also a possibility that the second photon will be produced by this, okay? The second photon might be produced like such that it is just out of phase with the existed photon, incoming photon, and this is what happens, and that it's deep, we match up with the peak of the incoming photon. In that case, you know, if this is such a case, you will have no any light in the medium, because when these two waves are summed, you know, if there are two waves which is at the same frequency, same wavelength, but their phase is out of phase. I mean, one dip has the other peak, and these waves will just destroys their intensities by just, you know, a process which is called destructive interference. Then in that case, these two waves will interfere such that when you sum them, you will have nothing. If you add these two waves, you will have just nothing. But if you add these two waves which are in phase, you have a larger amplitude. Okay, so I mean, what I'm trying to say is that if this is just a resonant photon, then the produced photon will be just a copy of the incoming photon. Okay, it will be copy in every respect. It will be copy of the present photon, just matching their phases also. Not only the amplitude, the frequency, or their phases will match up. Okay, all right. So, but you know, we have seen that in our previous slides, that an excited atom will go down their electron by producing a photon in any direction possible, in a random direction. It might be, you know, go in this direction, it might be going in this direction, it might be going in this direction, etc. But what you see over here, the produced photon is just going in the same direction with the previous photon. Okay, and this is the produced photon. Let's say this photon is created by the electron coming down, and this photon is the incoming photon. Well, if there is incoming photon which is right at the resonant frequency, the produced photon cannot go randomly in any direction. It must, or it will go just with the same direction of the incoming photon, the resonant photon. Okay, there is also subtlety over here, that this electron going down, if it goes down by the help of the resonant photon, then the produced photon will always be produced and going in the direction with the same direction of the excited photon. So this is called stimulated emission. I mean, this is not spontaneous emission. This is called stimulated emission. I mean, you might have an atom originally which has its electron in the upper level, and as I said, this electron will not stay there forever. It will go down, after nanoseconds. But if there are no any photons, existent photons around, when this electron go down, it will produce a photon which might go in any random direction. Okay, but over here, since we have an excited photon, the produced photon will not go in any random direction. It must go with the same direction of the excited photon. But over here, this is the case of spontaneous emission. In the spontaneous emission, there is no excited photon. There is no surrounding photon of the same frequency or resonant photon. Then in that case, produced photon will go any random direction. But in the stimulated emission, the created photon will always go with the same direction that of the existed photon previously. So you have then two different emission, and these emissions are different in such a way that the produced photons one in stimulated emission is going in a certain direction, but in the spontaneous emission the produced photon may go in any random direction. Okay. Alright, this is the second picture. It just refers to the classical case that you have the amplitude of an incoming light. Just amplitude is increasing by a certain amount because the atoms which are giving off energy from their electrons. Okay. Okay, next, what you see over here is that you might ask yourself that, okay, suppose you have a medium which has many of the atoms, and some of the atoms might be in the ground state, and some other atoms might be in the excited state. Okay, so if you have an absorber, this is the case. What you see over here in the picture. What you see over here is that you have more number of atoms which are on the ground state in compared to excited state. So an example over here that 1, 2, 3, 4, 5, 6, 9 atoms over here, but 6 of them is on the ground state, only 3 of them is in the excited state. So if you have an input light which is at the resonant, what I mean by resonant is the input light frequency is just matches up the energy difference between these two levels. What happens is that this medium will act like an absorber. Why? Because it has more number of atoms which are at the ground state than in excited state. So if you send the light, then in that case the amplitude of the light will be reduced because the probability of absorption because of these higher number of ground state atoms is higher than the probability of the probability of emission because of these excited level atoms. Okay, so in that case, let's call N1 as the number of atoms which are at the ground state, and N2 is the number of atoms which are at the excited state. If N1 is larger than N2, this medium will act like an absorber, and the process will be in the net absorption. But in the second picture, if you have exactly just vice versa, in the other way around, if you have more atoms which are in the excited state in compared to the ground state atoms, then in that case the input light will get amplified because the process of stimulated emission is having a higher probability than the process of absorption, because these atoms will absorb the incoming light, but these ones will emit. Stimulated emission will take place, but since number of atoms which are at the excited level is higher than the ground state atoms, then your incoming light will be amplified. So we have a net gain, we say, or we have just amplifier if N2 is larger than N1. And this case is also known as, in the laser literature, as the population inversion. Population inversion is just refers to the case that inside a medium, if you have more number of atoms which are at the excited level than in the case of ground state level, we have a population inversion. I mean, the population of the atoms which are at the excited level is, higher. Okay. So, at least, we have the first answer to our question that how does a laser work is that first condition we have found. That we have, remember, we have these mirrors, and inside the mirror we have the amplifier region. Amplifier region corresponds to atoms like this, and some number of atoms might be at the excited level, or some number of atoms might be in the lower energy level. And if you want that your optical resonator acts like a laser, the first condition is that the amount of or number of atoms which are at the excited level must be higher than the atoms in the ground state, and this case is referred to the population inversion. You must have first the population inversion in order to start your laser work. But of course we have the other conditions must be satisfied in order to start your laser working. So as I said that in order to start your optical resonator lasing, first you have to build up an optical amplifier inside this laser device between the two mirrors. You must have an optical amplifier, you must have a population inversion. But suppose that you have this medium which has only two levels of atoms. Suppose, there is no such a case that you have your atoms only having two levels for the electrons. There is no such an atom. But suppose you have a system of atoms, and atoms have only two levels, and you want to build up first an optical amplifier. So what you do is, initially all of your atoms tends to be, as I said, to be in the ground state. What you want to do is first you just bring these ground state atoms to excited level. And when you just pump, pumping means that in some way you give the energy to the medium so that the atoms which are on the ground state just excited to the higher energy levels, because you provide energy, energy. This energy might be an electrical energy, chemical energy, or heat, or something else. We will talk about this later. In order to start a laser, we must provide some energy, of course. Just like your ordinary laser pointer just uses a battery, small battery, to start. We need this extra energy, and this is referred to as pump. So you're pumping your ground state energy levels, ground state atoms, so that these are just pumped to high energy levels. But the thing is that if you start this, you bring up some of the atoms at the higher energy level, and at some stage the number of atoms at the low ground state and the excited state will be just equal to each other. But if you still continue to pumping, you will just see that this number, which are equal to each other, will not change at all. Even if you provide more and more pumping, after you reach this equality, that the number of atoms in the excited level and the ground state level, even if you pump further, you will see that if, of course, you have only a two-level atom, but in reality there is no such an atom. If you have only two levels, okay, you never reach a population inversion. Why? Because, as I said, when atoms are excited, these electrons will go back, because they tend to go back. But whenever they go back, because there is pumping, they will just receive again an energy. They will kick themselves to the upper level. So this equilibrium will not change at all, and the population inversion will not be satisfied. Okay, so here there is an important second condition, that if you have some medium of atoms which consist of only two energy levels, even if you have enough external energy to provide to your system, you cannot start lasing. Okay, this is very important. Even if you have enough energy, only with the two levels of atoms, you cannot build a laser. So in order to build a laser, you must at least have atoms which are having 3 energy levels. Okay, and this is one condition, that in order to have a laser, as I said, you must reach a population inversion. But in order to reach a population inversion, you must have at least 3 atoms which are having 3 energy levels in your amplifier. So suppose you have this 3 energy level of atoms, okay, and what you do is, well, one is the ground state, 2 is the second energy level, and 3 is the third energy level. Third energy level is at a higher energy level than the second energy, and just you see what you see, and in terms of energies, E3 is larger than E2, E2 is larger than E1. So, but in such a case, which transfer of electrons will produce laser photons? So, if somehow, again, you have a pumping mechanism so that you pump your ground state electrons or ground state atoms to third energy level, okay, not the second one but the third one. If you provide energies such that the energy is just matches up, the pumping mechanism matches up the energy level between E3 and E1, these electrons will just jump to the third energy level. But after reaching this level, there are usually 2 possible ways to lose electrons energy. They can first jump to the second level, and then from the second level they go to the ground state. This is one possibility. Or they will go directly down from third energy level to the first energy level, from third to let's say the ground state. Usually in in atoms of having 3 energy levels, the second case probability is very weak. I mean, the process that electrons will jump from third energy level to the first energy level is not allowed. Usually this is called the forbidden energy transition, and the reason is quantum mechanical. In fact, it can be understood that in order to lose the energy of these electrons, not only they must be at a higher energy level, but also this level and this level matches up in the spin or angular momentum, okay, and angular momentum also must be conserved. So this 3-to-1 process is forbidden because the momentum is not conserved. So they first go to 2, and from 2 to 1. Anyway, okay. So let's say the electrons going from third energy level to the second energy level. Let me draw it here. Suppose this electron goes to second energy level. Since it loses some energy, this energy will create a photon, right? And the frequency of this photon, of course, will be just E3 minus E2 divided by H. And this is F32, because we label as F32 because the photon is having a frequency just matches up the difference between the third and second energy level. So this is going to be a lasing frequency, okay? And your laser is just a 3-to-2 transition. But this one is also possible. 2-to-1 from 2-to-1 transition also can produce laser. Some lasers is working like this, but some lasers is working like this. So there are two possible way of making laser out of this 3-level system. So suppose this is the way, okay, and 3 to 2 transition produces laser photons. So as soon as you start this pumping, you now figure out that these electrons just going to third energy level, and there is no any electron in the second energy level. You see, the population inversion condition is just filled, because as soon as the first electron goes to 3 energy level, when there is no any electron in the second energy level, N3 is going to be larger than N2, so the population inversion condition will be satisfied. So this is the way to produce population inversion. In order to produce a population inversion, as I said, you must have at least 3 energy levels in an atom. So what you see in this slide is that now you have a 3-level system making up your amplifier, and you have a photon source, a variable frequency photon source, and suppose you put a detector over here. Just I draw a detector over here, and so you send light in such a way that your light frequency is just matches up the energy difference between 3 and 2, and moreover some other system is providing a pump to the amplifier, so that the amplifier atoms is making this from 1 to 3 transition. Okay, so that means you always have a population inversion, because you will always have some number of atoms which are at the third energy level, and some number in most of the case there is no any atoms which are in the second state energy. In that case you will have a population inversion. Okay, in this case this medium of atoms will just work as an amplifier. You will see that if you just send a light, input light, which just matches up the frequency to the difference between the third and second energy level, your detector will count a larger intensity at the output over here in compared to the intensity of the incoming photons. This is the intensity of the incoming photons, and this is the intensity of the outgoing photons. It is just this intensity corresponding to incoming photons, and it is just peak intensity corresponding to the outgoing photons over here. So you now have an amplifier. Okay, this is an amplifier, but it is not a laser. Okay, because you see there are no mirrors over here. In order to have a laser, you must have mirrors. So the next question is, how does a laser start? If suppose you have an amplifier. Now suppose you are given these 2 mirrors. You put these 2 mirrors to make up a laser. Okay, so next is, think of also, in addition to the atoms in the amplifier, the medium of atoms, which are, let's say, 3 levels of atom, you put these 2 mirrors. Okay, and you pump your atoms so that your atoms initially at the ground state will jump to the third energy level, and some number of atoms in the third energy level also. So they are expected to go down to second energy level, producing photons. All right, so what happens over here? What happens over here next is that when these atoms which are at the third level start making this transition from 3 to 2, in the process of spontaneous emission, they will just give away photons randomly in any direction. Over here, what you see over, for example, this just to represent the photons inside the medium or amplifier, we just represent over here, pick up only three atoms out of them. So let's say, for example, the first atom will just give off a photon in this direction, the second atom is giving off a photon in this direction, the third atom in another direction. I'm just picturing the random nature of this spontaneous emission, right? But the thing is that, if these are the mirrors, we must have a laser going just perpendicular to the mirrors, like this is the case. And over here, one of these mirrors, let's say the left mirror, is 100% reflective. No any photons when come over here will transmit through the mirror. But the second mirror, let's say, make it not 100% reflective, but there is some transmission probability. Let's say maybe half of the photons that come over here will pass through, half of them will be reflected. So this is not 100% reflective. Otherwise, you're not going to get some light out of this laser, and this is nonsense. Of course, if you cannot take away the photons, you will not have a laser, of course, right? Because you must have one of the mirrors, at least one of the mirrors, to let some portion of the photons let through them, so that you get the laser light out of the box, right? So. But this is not you expect from a laser. I mean, this picture is not the you expect from a laser. You expect from a laser a directed beam of light coming in one direction, not in every possible direction. Okay? You're not producing a light bulb. We're producing a laser, right? So in order to produce a laser, you must have all the photons or light coming in a certain direction. Without going away in any direction, we must have our laser in certain direction. So after some few photons produced in these excited atoms, you will see that the photons that goes toward the mirrors perpendicularly will start a process which is called, as we previously seen, the stimulated emission. I mean, these photons. So suppose this is the photon that goes through this right mirror, and this photon is going to be one of the photons in our laser, but not these photons. These photons are not going to be laser photons, but this photon is going to be laser photon. Why? This photon will start if it sees an excited electron over here. Let's say an excited electron, if meets up with this photon, this electron will just drop down to second level, producing the second photon in addition to this one, producing an extra photon, which goes exactly in the same direction with this photon. So now this photon will just copy itself a second photon, which is just going in the same direction, with the perpendicular to the mirror. And these two photons will initiate other two photons which are going the same direction, which is in this direction. And they will go back, if they reflect from the mirror, they will go back, accumulating more and more photons which are going in the same direction as that of this one. So when this number of photons that goes in certain direction, this direction that goes to perpendicular to the mirrors, will exponentially grows, so that after a while, the process of emission in this chamber, in this resonator, will almost 100% be stimulated emission, not the spontaneous ones. Because if the number of stimulated emission photons, that means if the photons are going only in these directions, in the directions which are perpendicular to the mirrors, is getting high and high, that means they will see more and more photons and electrons, the excited atoms, and these excited atoms will not find enough time to just radiate their photons spontaneously in any direction, but since they see almost all of these directed photons, they will produce the same direction photons. So eventually, after a while, a very short period of time, usually this takes a microsecond, okay? A microsecond, after microsecond, sometimes it might go to seconds or so, but few seconds. There will no any more spontaneously emitted photons inside this medium. Most of the photons will be not. I cannot say 100%. There will always be some of the atoms which are spontaneously emitted, but most of the photons, since inside the chamber there are many photons going in a directed direction, most of the photons will go in the perpendicular direction or the optical axis. So they will build up very high intensity after a while, after a very short period of time. They build up a very high intensity level, and after this level, of course, some of the photons will make through this mirror on the right hand side, because it is not 100% reflective. Some of the photons will just get through, and these photons will get through the second mirror, will be laser photons. Okay, so this is the way that to initiate the laser photons inside an optical resonator. After a very short period of time, one of the processes will dominate over the other process, and this is called the stimulated emission. The stimulated emission process will dominate after some short period of time the spontaneous, but initially the spontaneous process is dominant. Spontaneous process is the produced photons will be spontaneously produced photons, but very few of them will be directed photons which are going in the direction of the laser, and these photons will quickly exponentially increases the number, so that it causes the more and more photons which are going in the laser direction, and more, and eventually stimulated emission will dominate the spontaneous emission, and your laser will start lasing. So this is the process. Okay. So you see over here now, after some period of time, almost all of the transitions from 3 to 2 are now in the laser direction. Okay, in the lasing direction. No, you won't. Well, there will be some very few of them. You cannot say 100% all of the even the laser starts lasing. Some of the atoms will still emit some photons in other directions, but these are going to be very few. I mean, maybe only very small fraction of a percentage, maybe 1% or even less. So you see laser in action, because inside the resonator, optical resonator between the mirrors, the intensity of light is such a high level, so that the right mirror will just give off some of its photons outside, and this is going to be laser photons, which are practically used.